Hello. For this last part on the series of factoring quadratic expressions, I wanted to talk to you about some of the special cases that emerge. The whole thing about these special cases is they're just little minor exceptions that can lead to some shortcuts so that we can get to where we're going a lot quicker. In the first case is, a lot of times you might see the first term and the last term of a trinomial, quadratic form, they might both be perfect squares. 2x times 2x equals 4x squared, and 3 times 3 equals 9. So there's this test that you can do to say, hey, this might be a perfect square trinomial. And you know what that is in just a second, but I'll show you the test, and then I'll show you how it works out. The test is, you take the square root of the first term, which is 2x, you take the square root of the last term, which is 9, or which is 3, and you multiply that by 2, you double it. The number you get, 12x, if that is the same number as the middle term, then this is an example of a perfect square trinomial. What you're allowed to do is, if you identify that as a perfect square trinomial, is simply jump to the factors. There's going to be two factors of 2x plus 3 times itself. I don't know why I put a 3 there. It should be a 2. There we go. Let's get rid of that 3. Boom. There we go. So just looking at the original process then, what we would have done, if I didn't recognize that as a perfect square trinomial, I would have had to establish my x box, where we put the 36, which is the product of 9 and 4, into the top number, we put 12 at the bottom, and we get 6 and 6. Here's a clue. If you're using x box and you find these two numbers to be exactly the same, that's another test. You have a perfect square trinomial. I was able to do that without having to multiply 4 and 9, but whatever. Anyway, the old-fashioned way of factoring this would be to take the middle term 12x and break it up into 6x and 6x, so we could be 6x-ful. And then we just do the regular factoring algorithm, and we end up with two identical factors, which is a perfect square. So we could do all of this work if we want to, but if we have the presence of mind to identify a perfect square trinomial, then I'm totally okay with you identifying that and then putting in the shortcut. So try this test again for 100x squared and 4. 100x squared square root is 10x, and the square root of 4 is 2. 10x times 2 is 20x. You double that, you get 40x. Is that the middle term? Yes, it is. Then 10x plus 2 quantity squared is my perfect square factors. Keeping in mind here, of course, we could take this one step further and take out a 2, leaving us with 5x plus 1. All of that is squared. So we could also say that that's equal to 4 times the quantity 5x plus 1 squared. That's fully factored. But that's for a later day. We'll deal with that kind of stuff. All right, so let's try that test one last time. This is a perfect square, and that's a perfect square. So we try the 2x, and we try the 3, and we double it, and we get 12x just like we did before. But I notice my middle term is 13x. So that means this is not a perfect square trinomial. That is not to say that it's not factorable. It just means I can't use my very abrupt shortcut to factor it. I have to go back and do the old-fashioned way. So we choose 9 and 4 to break up 13x. We into 9x and 4x, and then we factor by grouping, just like we did before. All right, the second kind of special case is what we call difference of squares. That is to say, if the first and last terms are perfect squares and they're being subtracted, that is a candidate for difference of squares. It makes logical sense. And what happens when you have difference of squares is essentially you're going to have one of each factor. The square root of x squared, which is x, the square root of 9, which is 3, and then we'll do x minus 3 times x plus 3, and we'll get that. Now, if you notice how I FOIL this out, we're going to have x times x for x squared, we're going to have x times 3 for 3x, negative 3 times x is negative 3x, and negative 3 times 3 is negative 9. Look what happens to the middle terms. 3x minus 3x is 0. So that's why with a 0 term, there's no middle term in there because the coefficient was 0, and that's how we know we have a difference of two squares situation. So here, 4x squared, is that a perfect square? Yes, it is. 2x times 2x. 81 is 9 times 9, so this is a difference of two squares situation. I write 2x plus 9 times 2x minus 9. It doesn't matter which order. Now finally here, I recognize 9x squared is a perfect square, and so is 16. However, they're being added together. If you think about it, we could try to say what the middle term has a 0 coefficient. 9 times 6 is 144. What numbers multiply together to give me 144, but that will add up to 0? Well, it's impossible, basically. I'll save you the trouble. And so that last expression, 9x squared plus 16, we call it prime because it's already reduced to all the factors possible. There are no smaller factors that would make up the number 9x squared plus 16, so it's prime. For this last bit, I just want to remind you that factoring as an act is simply just breaking something up into its component factors. So to factor x squared plus 9, I could write it as x minus 3 times x plus 3. I broke it into factors. Factoring the number 20, you can factor, or I'd say the number 22 can be factored into 11 times 2. So I just did factoring. So this whole thing we learned here with the whole X box and the factor by grouping and that process, that's a process that helps me to factor. But that's not all of factoring is. Factoring is a whole bunch of different things. For example, we could do some shortcut factoring and recognize perfect square trinomials. We could also recognize difference of two squares and do some more shortcut factoring. But here, this is even better. All I have to do here is find common factors. There's no other trick to this. It's just what goes into both 5x squared and 25x, the answer, 5x, leaving us with x minus 5 left over. Now I've taken this and broken it into two factors. Did I use the x box method? I did not. I just took out common factors. Simple as that. So once again, in the next expression, 4x squared minus 12x, and take out 4x, leaving us with x minus 3. Notice if you FOIL back, or distribute back, you get right back where you started. And last but not least, we'll take out a 2x from the last expression, 2x cubed, I think, and that's going to leave me with a 10x, not a 10x, a 5x plus 1, because 2x cubed was taken out. There's a 1 for a placeholder. A 2x cubed divided by 2x cubed is 1. Hope you find this helpful. Thanks for watching.